Everything we've done so far in differential equation solution has been from one single starting point. We, through one method or another, whether it be some simple Eulerian estimation or whether it be through sequential averaging of slopes or Runge-Kutta re-estimation of slopes at some future points, it's all been in search of how to properly place this next estimate of the state for some eventual sequence that describes the solution to the differential equation. But what if we're in a circumstance where we already know the first 4 points of a particular solution, and we want to use that historical information to improve our future estimates of the differential equation? Why only take knowledge at that point and maybe some of its future derivatives? Why neglect all of this history that could help us predict the future form of the equation? These are called multi-step methods, where they take knowledge of not just the point you are at, x of I or x of p, y of p, but you also look forward or sometimes backwards points to figure out a better estimate of the differential equation evolution. So the principal method the book discusses in multi-step is Adams-Bashforth, and then we go into a implicit method called Adams-Moulton. But first, Adams-Bashforth looks at historical points. So this first case is just second order, which means 2 points. It's kind of like doing a second order integration. This is kind of the ODE equivalent of Simpson's rule for integration. But look, so you take the y value, the state value you're at, plus half the step size times 3 of the functional evaluation you're at, minus the functional evaluation of the previous step. So whereas everything else we've done so far in this chapter was just dealing with starting point x, I, y, I, and then shooting derivatives out into the future and trying to predict the performance of that equation based on just one source point, this is making use of previous knowledge. And that gives you a decent estimate of y of I plus 1, if you have that knowledge. If you only have one initialization point, you can't possibly know what happened in the past. So you'd have to perhaps seed a series of initial points with Runge-Kutta, fourth or fifth order, and then seek to, after that, use progressions based on these formulations on Adams-Bashforth. Now, of course, a third and fourth order equivalent for Adams-Bashforth exists. Third order, as you expect, takes 3 total points. So you're looking at the point you're at, the point you used to be at, and 2 points ago. So it uses trailing information. As you might expect, the fourth order just takes it one step further. The point you're at and the previous, second previous, and third previous points, except look at the weighting. So 55 times the first, 59 times the second, 37 the third, 9 the fourth point, which is 3 points back in history. So these are fairly decent estimates of future states of the differential equations. But there's a way we can do it better. Adams-Moulton is implicit. Let's look straight at the description. Notice that I say it's implicit because you take the point you're at and the point you're going to figure out the point you're going to. So all you have to do is know where you're going to know where you should go. That makes sense, right? Here's that implicit problem again. You could go through this iteratively. You could guess a future point, put in the equation, see what future point you get, and hopefully it converges, which, actually that's kind of what we end up doing. But we make it sound better than that. The third order looks at the point you are, the point you used to be, and the point you're going to. Notice that none of the Adams-Moulton methods go more than one step into the future. They're all at least one step future and one or more in the past. So the fourth order method is 1 into the future, the point you're at, 1 into the past, 2 into the past, with the appropriate weightings therein. So again, you have to have knowledge of those previous points, and somehow you have to obtain knowledge of the future. So the algorithm for doing this is that you use a method, an explicit method, to determine y of I plus 1. You might as well use Runge-Kutta. It's fairly simple to implement. The algorithm is somewhat low intensity. And then so you put that estimate into the second, third, fourth, pick your variety of Adams-Moulton methods. Of course, you probably have to pick based on the availability of points in your data set. So you substitute that future estimate, and then once you have a future estimate, well, you take the output of Adams-Moulton to improve your future estimate. And you essentially create this circular loop until the output of Adams-Moulton, per se it's fourth order Adams-Moulton, the output is fed back in, you recalculate the output, which you feed back in, and recalculate it, which is the output, which you feed back in. It should converge until what you're feeding back in, what you're getting back out are essentially the same number. So if you feed it with a decent seed, y of I plus 1, then you should be able to use this type of update equation, predicting and correcting the differential equation solution to converge on more or less the truth numerically. Now in the example that follows, the predictor-corrector circumstance, they use Euler's explicit method as a predictor, and they shoot it out into the future. And I suppose that works, but Runge-Kutta, once you program it once, it exists, it's there, it's easy, may as well use it. So I'm always a fan of getting the best initialization you can. So this is actually a very powerful method of sequential improvement. Seeing that I portrayed Runge-Kutta as a famous numeric method, which it pretty much is. It's being taught all across the country. Any decent numeric methods class teaches you how to use it, how to implement it. It makes sense that MATLAB has multiple algorithms that can do ODE solutions using it. So even your textbook, straight off the bat, says start with ODE 4.5. This is actually a MATLAB algorithm that uses Runge-Kutta methods based on the fourth and fifth order explicit forms to update your differential equation. They have reduced order methods, ODE 2.3, ODE 1.1.3. Some of them are predictor-corrector. Some of them are, notice it works here with Adams, Bashforth, and Moulton methods to improve estimation. But you might as well start off with the big guns because it's not actually that hard to calculate. Especially if you're not calculating anything, you're just telling MATLAB to do it. So just know that MATLAB has inbuilt functions for calculating these solutions. In every single case, they will ask you to define generally a function that gives you the output. So whether that's an anonymous function or however you are delivering the functional evaluation to the ODE solution method, you're going to have a way of updating the slopes. Also keep in mind that you have to take any differential equation of an order greater than 1 and reduce it down to a multitude of first order equations. If it's a second order equation, you're going to have 2 first orders. If it's a fourth order equation, you have 4 first orders, so on and so forth. It has to be in that form for these ODE solvers to figure it out. So some of those stand-in equations could more or less just be identity equations. They could be definitions, which are absolutely cake and simple to determine once you're used to it. I mean, to learn it takes some trying, but know that they have to be fed first-order differential equations. Know that these algorithms are already pre-programmed if you need to use them. And that's it. Time to go to some examples.